Good afternoon. This is CIVE 638, Sedimentation Engineering, and this is class number 122 for 12-2, meaning 12 weeks, second lecture. And I'm Professor Victor Ponce with the Department of Civil Engineering at San Diego State University. And the subject today is we're going to wrap up the modified Einstein procedure and then proceed to the next section, which is reservoir sedimentation. So I'm going to finalize the presentation on the calculation of bed material transfer by the modified Einstein procedure, and then move on to talk about the Lara modification. Briefly talk about the Lara modification. Okay, so I'm going to rerun this so that I can show you, and I believe I did my work this morning, and I'm hoping I didn't reset it or anything. The discharge 230, 208, this is the standard input for the modified Einstein procedure. Normal size fraction, the fractions of bed material and suspended, and then we're going to do USBR 1955. There it is. Let me do the calculation. Good, these numbers are correct. I think I already told you that the number 418.3 is exactly the number that it's written or it's presented in the table that it is attached to the document that we are reviewing. And unfortunately, I already shared with you the fact that I can't find, or I don't have the table, but this is, believe me, this is the table that is in the book. And we made sure that all the calculations were done correctly, step by step. Okay, so that's so now what I'm going to do in here now is to go on and just dwell a little bit on the properties of this procedure. And with that, I go to the sample input. I don't really need to go to the sample input because that's the sample input that I already did. Rationale, that's very important. The rationale behind the references. And by the way, you can see the references in there, the Einstein bed load function, the Kolbe and Hembry method. We've seen briefly both publications, 1950 Einstein, 1955 Kolbe and Hembry. And then with 1955 is the actual document that we have been reviewing that we covered last Tuesday. And then the Lara publication, 1966, Bureau of Reclamation computation of C primes, that we're going to be seeing today. Okay, so we're going to go to rationale here first. Make sure we understand the concept of the methodology. And why is it that it's been said that it is the best method available? The modified Einstein procedure computes, let me just go in here for a second. That doesn't want that way. Okay, there we go. Computes total sediment load consisting of bed material load and fine material load, wash load, by individual size fractions. It computes the measured and unmeasured portions of the total sediment load. How does it do that? Well, because the method has input data of concentration of sediment concentration, but we recognize that the total measured sediment is not the total transported sediment, because there's a portion at the bottom of the channel that cannot be measured by the sampler, short of hitting the bottom and then disturbing the whole thing and then messing up the measurement, right? It's been said quite correctly that every measurement has its limitations. And this is one of the limitations of this particular type of measurement, that you cannot reach the bottom because you'll mess up the measurement. Okay, as such, it is the most complete method of calculating sediment load. Okay, now to be honest with you, none of us know exactly how these gentlemen develop this stuff. And I am curious about how they develop the fine material load in here, because we already stated many times that that's not hydraulics, that instead it is hydrology. In other words, it will vary with the location. So So I am trying to guess here, and I do believe that what they're doing is that they're analyzing the samples that were measured at the Niobrara, and they were coming up with the transport, the fine material transport at the Niobrara. I'm going to be looking into a little bit more in detail, and I'll report to you later, because it just occurred to me this morning that I was reviewing this, that how is it that they're going to assess the wash load, the amount of wash load, which is hydrology, not hydraulics. But they had done it, you know, to their record, or in recognizing what they have done, they did it and they stated it that way, because all we're doing here is we're stating what they said. The procedure requires the following inputs: hydraulic flow variables, right? All of them, as we have listed just recently, the bed material sizes, the measured sediment concentration, the bed material fractions in each of several size ranges, and the percentages of the fractions in size ranges, right? And the percentages of suspended material in each of several size ranges. All that stuff is put together and is in the example in the 1955 STEP method Bureau of Reclamation publication. And so we consider the following as a general statement. Given sediment transport formula computes only bed material load and not fine material load. But they are doing this. A given sediment transport formula may not be strictly applicable to the site of interest. Right. In this case, it is applicable presumably because they're actually doing the measurement at a site. A field measurement with a suspended sampler provides a measured fraction of sediment load, but not the total load. So what they're doing is they're using the Einstein formulas to extrapolate toward the bottom, because they do an integration at the bottom, an integration of the concentration of sediment times the velocity. And that gives them a discharge, a solid discharge, a suspended discharge, or rather a sediment discharge. The unmeasured portion of the sediment may be a substantial fraction of the total sediment load. Yes, we estimate roughly 20%. It could be 10 or it can be 30. You know, there's also variation. But 20% is a good working number or ballpark figure for the unmeasured portion. The modified Einstein procedure is based on the Einstein bed load function. That is true and correct. That is why it is called modified Einstein. Modified Einstein procedure computes both bed material load and wash load and accounts for both measured and unmeasured loads. That's the issue of the if that I said this earlier today. Thus, the modified Einstein procedure eliminates the shortcomings inherent in sediment transport formulas and field measurements of sediment load. Given the proper front end, back end conversions, the modified Einstein procedure can be used with SI units, because the method was developed with US customary units. But we have allowed the calculation in metric or SI units to be done. It's fairly straightforward. You don't have to change anything but the front end, back end. In other words, the input, if the input is SI, as it gets into the computer, it gets converted to US customary. Then the output is US customary, and at the end, you convert it back to SI. And that is why in our methodology, there's 24 columns in US customary, and then the 25th column for the SI is the answer in SI, in metric tons rather than in just tons. Okay, given several sediment load measurements at different flow stages, right, the modified Einstein procedure can be used to develop a sediment rating curve, a curve of total sediment load versus water discharge. And I did show you as an example the sediment rating curve that was presented by Covey and Hembry in their 1955 report, which is a very good, solid, how can I say, veritable set of data, because it was done by the best. They were the best at the time anyway, Covey and Hembry. So total sediment load is bed material load plus fine material load. We have defined that from the beginning. Total sediment load is measured sediment load plus unmeasured sediment load. And we are now defining it in addition. So total sediment load can be expressed both in terms of the type of material as well as the comparison, or rather putting together both the measured and unmeasured. So that's it as far as the procedure. And now we go to the features. Total sediment discharge by the modified Einstein features. When we have a complex methodology, we always try to do this. In other words, additional pages to the main page that runs the model, so that users won't have to go back to the original references. Okay, so number one, the fall velocities are calculated using Ruby's formula. And while I did not present to you Ruby's formula, you can find it on the web. It can be found on the web or in any other reference. You just Google Ruby's formula and spell it that way. Don't spell it any other way because you wouldn't get there. RUBEY's formula, sediment, it's there. And we use that formula in the computer program, as well as Hobie and Henry used that formula. Also, we follow what they did. In SI units, input is metric and the data is converted to US units for internal execution. That's what I already said earlier. Output from columns 1 to 24 is the same for both system of units. We didn't attempt to change the method before we did the calculation. I felt that it was safer. And this is the way we've done it all along. If we have a method that has been developed consistently in American units, or rather US customary units, we're not going to change it. We'll just produce it and then we'll change it at the beginning or at the end, as the case may be. Okay. The program can take either two sets of size fractions, normal 9 sizes and long 10 sizes. We did that in order to follow the procedure and the data that had originated by Hobie and Henry. Viscosity versus temperature table is given by Lindsley, which is a standard reference in chemistry books and stuff. I've checked. It's the same table. Everybody uses the same table. It hasn't changed in 50 years. It's the table of kinematic viscosity versus temperature. For that matter, kinematic or dynamic viscosity, because you know there's a direct relationship between them. That's also part of my book, by the way, because in my book, we needed to have that. So in the appendix to my hydrology book, this table is in there. And of course, in order to put it on the computer, we had to digitize the entire table, which is, well, it's not something that people look forward to doing. It can be done, and it is done. It's a whole lot of numbers that have to be digitized. The reference size fraction is chosen as the diameter that has the largest percentage of suspended load. This is the crux of the matter in the methodology. One of the size fractions has to be chosen as the reference so that the others, the computation of the Z prime of the others is based on the reference. The USBR 1955, the original method for the computational, or rather for the computation of Z prime, which is the exponent of the it's the exponent that used in the computation of the, I'm losing it in here, in the standard, the reference size. Okay, is the ratio of computation say the ratio of C prime for each size fraction to Z prime for the reference size, right, is equal to the ratio of the respective fall velocities to the 0.7 power. How did they get this? I don't know, to be honest with you. We follow what they're doing. However, this concept has been, I should say, argued by other people later, and that's what we're going to cover in a minute here. The fall velocities are calculated by Ruby's formula. The multipliers are the ratios of the fall velocities to the 0.7 power. That's the original procedure. Given Z for a reference size, estimated by trial and error, and that's a procedure explained in the publication. Remaining C's in column 14 are calculated using the multipliers. That's already been done and calculated. I may not have spent a lot of time on it, but you can, on your own, look at the table and you'll see that that's the way it is. The USBR Z computation is implemented in a somewhat different way. Let me put my 2 cents worth in here. What happened was that in 1955, Hobie and Henry developed the Z computation based on the Ruby formula, and it is a 1-point methodology based on one diameter, one reference size. Time went by and people in the Bureau of Reclamation, continued to use the methodology beyond the experience that Covey and Hembry. And I'm not going to tell you what happened to Covey and Hembry, but obviously people do retire. I'm very well aware of that. And they go somewhere else or they do something else. So in the early 60s, there were people in the Bureau, they were doing these computations and they came up with the idea, or they developed the idea through a lot of experimentation and work, that the weak part of the methodology was in the computation of the Z prime. So because it was based in only one diameter and used as a pivot to the others, the smaller and the larger. So they argued and they came up with a methodology which is somewhat different. It is called a Lara methodology for the author of the paper, which we're going to review in a minute here. So the Z is found by the Z prime R is found by trial and error, and then a value of Z prime R plus 1 is found in the same way, and these two values of Z prime are plotted against their respective fall velocities, and to find a line, it's actually it's not a line, it's a curve, but it's a line if it's log cycles. Okay, so it's this equation here, Z prime equal alpha fall velocity to the beta, and with the alpha and the beta, then with that relation, once this relation has been determined, then we can calculate Z prime for all the other size fractions. That's called the Lara methodology. The multipliers are not used. So as you can see, now what's going to happen is that when we apply this way of calculating the C primes, the procedure is going to give you a different answer. Which one is the better one? Presumably the latter one. Otherwise, they would not have done this work, and they would not have presented that work in such forthright manner, right? If they had any doubt. So it seems to me that the method to use is the 1966 method, not the 1955. However, we wanted to keep straight on this, and we presented both. No big deal. I mean, to change the 5% of the methodology once you've got the 95% is no big deal. So that's what we did. We meaning us, the ones that developed the digital version. Okay. Caution. And there's a couple cautions in here. And the cautions are given because no matter how much care we put into coming up with these calculations, there is always going to be ifs and buts. Once you get going, you'll see that, oh, what happened? The problem doesn't want to work, or they're giving me what appears to be not the right answer. So you got to spend some time, and time means hours, days, examining the situation, testing this, testing that, until you come up with the right answer, what you believe at that time is the right answer. For instance, what we say in here for the caution, and I put these cautions in here because it has happened to us. For the USBR Z method, the reference size fraction, 1955 Z method, in other words, the original method. The reference size fraction is that with the largest percentage in column 11. This requires that column 7 and 11 be greater than 0. Otherwise, if one of them is not greater than 0, it doesn't work. You can't pivot because you don't have a place to pivot. Okay, then for the USBR 1966 method, Z prime method, the two size fractions considered are the reference size fraction and the next larger size fraction. This requires that column 7 and 8 and 11 be greater than 0 for those two size fractions. That it requires a little more consideration in the data. Otherwise, it's undefined. You can't draw a line through one point. The other point doesn't exist, then you cannot draw a line. And in this case, we're drawing a line through the trend of the data so that we can come up with the trend or the remaining values for the others. Okay, in other words, for the USBR 1955 option to work, there should be at least one size fraction for which there is both sampled bed material and sampled suspended bed material. It is also desirable that the chosen reference size fraction have a substantial sample bed material. Likewise, for the 1966 option to work, there should be at least two size fractions for which there's both sample wet material and sample suspended material. In other words, the data should be kind of good looking, because if it's odd and not well behaved, it's not going to work. It's going to work poorly. Default system is US customary. Okay, so that is it. We already went through the rationale and the procedure, right? If we go in here, yeah, we already did this. So we're gone. We're done here. Right, we're done. Okay, so now we go back in here now. Okay, we are fine. So now we're going to finalize this section by briefly looking at the Z, what I have called the Lara methodology, the computation of Z's for using the modified Einstein procedure. Computation of Z's for using the modified Einstein procedure, June 1966, Division of Project Investigations, Hydrology branch, Sedimentation section. This is in Denver, Colorado. And I mentioned this, although this report was not authored, it says in there, prepared by Joe M. Lara, hydraulic engineers. Okay, so briefly, as Lara argues in here, determination of the Z value is one of the several factors in the procedure that must be made. Z is defined as a theoretical exponent for vertical distribution of sediment. The original modified Einstein showed this value was determined by trial and error based on the data of a selected reference size. Values of Z for the other size ranges were then computed in proportion to the 0.7 power. Subsequently, Bureau of Studies disclosed that determining the Z value was not always representative. There were pronounced deviations in the computed values when the Z power was applied. It was concluded that this exponent uniquely described the conditions on the Niobrara River. In other words, they said the 0.7 is a Niobrara River characteristic. And of course, we're going to try to use this methodology for other rivers. So they changed the procedure and they developed a new Z procedure. This is on two diameters and so forth. So I'm not going to get, it's over. That's it. We already discussed it. We already said that over here, it says log was made of the relationship Z as a function of the fall velocity. Values of the fall velocity were determined for each of the geometric means, etc., etc. We know that already. The equation for this relationship can be found through fitting a curve, for fitting a line, a curve actually. Curve fitting here. The line of best fit for the equation can be computed by the method of least squares, right? That's standard stuff. By the way, in the method of least squares, the standard stuff, we have several programs for the least square, and one of them has been placed into the model. For the plotting, the Z values can be determined for the other size ranges from the plotting. The Z values can be determined for other size ranges having a percentage of material only in the suspended sample or only in the bed sample. In other words, it's an extrapolation, but an extrapolation based on 2 points. Recommendations. The procedure described in this paper to determine the Z value is recommended for use in computing the total sediment load by the modified Einstein procedure. So that is what they're recommending in 1966. And if I am okay in here, no, I lost it. I think I lost it. Let me see. Yeah, I did lose it, but there's no problem. We can go back very quickly because I've got the data in there. So I'm going to go back and run both of them so you can see. And the data is already here, so it's no big deal here. I'm really surprised that they chose to use this river, which is so shallow and so wide. I already told you 1 foot depth and 113 foot wide. That's unusual. That is high aspect ratio. But I'm not going to second guess them. I wasn't there, as I mentioned many times. Normal over here. We have this in here. Over here, USBR. So the answer to this problem is going to be 418. That we already know. Where is it? Here. 418.3 tons per day in American units, US customary units. 418 tons in the Niobrara per day based on the data. Okay, now we're going to run the 66, the Lara methodology, the one that runs a line instead of pivots around a point. It has two points that determine the line, and therefore the data is already determined. But what did I do? I stopped share. I made a mistake. I'm sorry. Apologize. I was too quick. So now what are we going to do? Is everybody now watching what I'm doing? Everybody now watching what I'm doing?
Yes.
Yes?
Yes.
Okay. I lost it there for a minute. I apologize. Okay, so we're going over here now. Remember 418.3, okay? Now we're going to calculate in here, and we get 462. So the new methodology has increased from 418, so 41. It's about 10%. 10% more transport with the Lara method, which is based on 2 points for the determination of Z prime. Is that odd? No, not at all. It's within the normal expectation. I think I already said, and I'll repeat it based on experience. It is our estimation that when you do a hydraulic computation, like Manning's in, if people give you the Manning and they went to the cross-section, you can't make a mistake because everybody knows the answer. So 1 or 2% would be appropriate. More than that, it is in error. But in hydrology, given the fact that hydrology is a little fuzzier, you can have 10, 20, even 30% error in hydrology. There's even larger errors. I know for a fact that, for instance, in evapotranspiration, the computation of one method vis-a-vis another method could be in error 50% or even more. The Thorne-White method gives much different answers than the Penrose-Monteith, for sure, in most cases that we have tried it. And that's evapotranspiration. And in sediment transport, as I already explained to you, because of the wide range of variability of the variable, which could typically vary 3 orders of magnitude, if not more, then allows us to be a little humble in terms of accepting the accuracy of the computations. And I have said in the past that 100% would not be inappropriate. So if one of you got 100 and the other one got using another method got 200, we could go back to the plotting by Professor Julian, which I have shown you as part of our syllabus, that there's wide variations in the methods depending on what formula you use. So therefore, we should be very careful and study the situation to make sure we use the right formula for the application, for the given application. Okay, with that, then I have completed this section, and I am now going to go into the next section, and I will begin the subject of sediment deposition in reservoirs. So let's get going in here. Sediment deposition in reservoirs. This is part of section 13.4. It is actually section 13.4 in my book. We're going to go over this today. That's right. Section 13.5 is sediment measurements. We'll go there in a couple of weeks. So we're back in here. Sediment deposition in reservoirs. Very complex problem in terms of societal requirements, because we would love to hold on to the water to be able to use it, but we do not like that the sediment is being settled at the bottom of the reservoir. Nevertheless, there's nothing we can do about it. All rivers that are self-formed are going to carry sediment. We cannot take the sediment away. If we take the sediment away, it's going to happen what has already been determined, that there will be hungry water and there will be erosion and so forth. There's a balance in there. We cannot stop the movement of sediment. All we can do is try to fix it, try to live with it, try to do something about it. As to what do we do after 100 years of dam use when the sediment actually fills up the dam? Well, we can do two things. We can either abandon the dam and go somewhere else, or we can hope to remove the sediment and put it somewhere else, because as you know, the sediment is not bad. It's just bad if we think that it's bad in a certain place, but not in other places. That is a fact. That leads to the concept of good flood, bad flood. A good flood is one that brings a sediment where we want it to be. And as you can see, the concept of sediment engineering has been around for, gosh, at least 100 years. And since Einstein, 1950, it took a life of its own. But it is something that those of us that have experience in this subject realize that we can never beat the sediment. We have to live with it. It's there. It was brought in by nature, and we can do the best we can. And it's not going to be in all times, in every time, it's not going to be the best for everybody. So we have in here a picture of the longitudinal sedimentation patterns in a reservoir operating at constant water level. And by the way, I do want to mention, since I'm at it, that in California, we had a couple of instances here where the dams have been declared to be obsolete or too old, and society has moved in and removed the sediment and take it somewhere else. It can be done. It's costly, it's a difficult job, but it can be done. So concepts of sediment yield and sediment transport are essential to the study of sediment deposition. Sediment is first produced at upland and channel sources and then transported downstream by the action of flowing water. If the flowing water is temporarily detained, as in the case of an in-stream reservoir, its ability to continue to entrain sediment is substantially impaired and deposition takes place. This is interesting because I'm saying in their in-stream reservoir. What's this thing? In-stream reservoir, where there are two types of reservoirs, in-stream and out-of-stream. And the out-of-stream reservoirs are now meaning in the last 20 years, preferred over the in-stream reservoirs because they have a tendency not to collect as much sediment. Because in-stream reservoir, you're going to stop all those sediment that's coming down, and it's going to deposit, and eventually, rather quickly, comparatively speaking, you're going to fill the dam. You don't want to fill the dam. We are typically building the dam to hold water. And if the dam is full with sediment, it cannot hold any water. That goes without saying. Okay, sediment deposition occurs in the vicinity of reservoirs. Typically, there's a bug in there, it's a comma. Typically, as shown in figure 1320. First, deposition of the coarser fractions takes place near the entrance, in that area that's called topset beds. As water continues to flow into the reservoir and over the dam, the delta continues to grow in the direction of the dam until it eventually fills the entire reservoir volume. First, let me observe that this graph in here is not at the accurate, or rather exact scale, horizontal versus vertical. Typically, when we do this, the horizontal scale is much reduced and the vertical scale is exaggerated. So this is just to show what is actually happening in a clearer way. The process is quite slow but relentless. Typically, reservoirs may take 50 to 100 years to fill, and in some instances up to 500 years or more. There's some reservoirs that have been operating for more than 100 years and they're still not full. On the other hand, there are some reservoirs which are properly called sediment detention basins that are supposed to fill in one event. They're designed for the stoppage of sediment when there's a whole lot of sediment coming down. An example is in the dam, or rather the sediment detention basin that was built in the year, what year was that? It would have been like 1990, exactly, 1991, exactly. In Santa Barbara, they had a fire. The fire of July 1990, you can check it out on the web, fire in Santa Barbara, 1990. And it burned a whole lot of acreage out there. And by the way, there's a lot of fires out there all the time. Near Santa Barbara, in the vicinity of Santa Barbara, not precisely in the city. And the problem in this case is that they have a lot of chaparral out there. There's chaparral country out there. Chaparral covers all the way from the vicinity of San Luis Obispo, going north of Santa Barbara, all the way to northern Baja California in Mexico. That's chaparral country, one of 5 sites throughout the world. Interestingly, why is it that we have chaparral only in 5 sites throughout the world? That has to do with the latitudinal, right? Latitudinal and exposure to the wind. So it so happens that if the ocean is on the left side, and if you are in certain latitudes, usually subtropical, around 30 actually, around 30 degrees, plus and minus, north and south, you're gonna have the chaparral, and you're gonna have fires, and after the fire, you're gonna have the debris flows, for the simple reason that the chaparral survives by virtue of protecting itself against exaggerated evapotranspiration by covering itself with wax, naturally speaking. And then when they cover themselves with wax, when it burns after a fire or during and after a fire, the wax dissolves and it hits the ground and it stays there, and it creates a non-wettable layer of soil. And that's what leads to the debris flows. And what is a debris flow? A debris flow is a movement of sediment that moves, say, 2 inches of soil in one event, when typically the 2 inches of soil should be 1 year or 2 years. So it's a huge movement of sediment. So since we know this for a fact from experience, that this is something that affects the California chaparral country, engineers typically want to avoid the debris flows because they could cause a lot of damage, all kinds of damage. So the way to protect yourself or society against this is to immediately after the fire to create a reservoir that will hold on to the debris flow. And that has been done successfully, by the way, in many instances. I happen to know of one particular instance in the 1990s, as I said, in the 1990 event. They had a huge fire in July of 1990, and then they had a huge rain in March of 1991. And I don't know if the relation between one and the other, but you don't follow fire with rain if you don't want to have a lot of trouble. And that's exactly what happened. Fortunately, the people that were in charge, among them some friends and colleagues of mine, and students, as a matter of fact. We had a student from San Diego State that went on out there to work with the Santa Barbara County Flood Control District, and he was in charge of the design of the dam back in the year 1990. So they shared the information with me, and I visited with them and so forth, and they were indeed able to protect the downstream portions of the watershed from excessive damage due to the debris flow. The flow was retained by the debris dams. Not sure if I have videos of that. I do believe I actually do have a video. I'll see if I can pull it out. Okay. The rate of sediment deposition in reservoirs is a matter of considerable economic and practical importance. Since reservoirs are key features of hydroelectric and water resources development projects, the question of the design life of a reservoir is appropriate, given that most reservoirs will eventually fill with sediment. In an extreme example, the filling can occur in a single storm event, as I just got through describing you the experience of 1991 in Santa Barbara. On the other hand, the reservoir can take hundreds of years, in the case of large reservoir located in a predominantly humid or subhumid environment. Because in the humid and subhumid environments, there's not a whole lot of sediment movement, so it takes a much longer time for that to happen. I have a picture in here, which is an interesting project. Sediment detention basin at the confluence of Arroyo Pasajero with the California Aqueduct near Coalinga, California. Okay, So what happened here was, and I do believe this project, I took this picture maybe 15 years ago, and they probably did this 30, 40 years ago, this project. The project had the objective of eliminating the problem, the sediment problem, in the confluence of Arroyo Pasajero with the California Aqueduct. The belief was that Arroyo Pasajero was going to carry a lot of sediment eventually, because it is in a situation, both geomorphologic as well as everything else, which it could carry a lot of sediment. And what the designers, and actually this is the California Department of Water Resources, they are the designers. The Department of Water Resources didn't want the Arroyo Pasajero to dump a whole lot of water into the California Aqueduct, which, as you guys know, the aqueduct, the California Aqueduct, brings a whole lot of water from the north, from the two dams up there, from Shasta and Oroville, I believe. Oroville, by the way, almost breached and broke 5 years ago. You must have heard of that. Everybody heard of that. So they designed this detention basin. So this is a detention basin. And right beyond this, beyond right there to the right, over here, right beyond this levee, or in the back of this levee over here, is the California Aqueduct coming south from Northern California to Southern California. Suffice it to say at this point, if you haven't figured it out already, that without that aqueduct and a couple of other large channels bringing water from the north, we would not be able to sustain ourselves here in Southern California. We actually get water from the north and from the east of the Colorado, which goes mostly to San Diego and to the Imperial Valley. From the north, it goes to Los Angeles, but we get it all the way from Shasta Reservoir, which is in the smack middle of Northern California, actually off north, because it does rain a whole lot out there. And there's not that many people. Interesting, how fascinating that the people are living here in the south where there's no water. And up there in the north of California, where there's a lot of water, there's hardly anybody living out there, right? The town of Eureka, which I have visited at one time, and other towns, but I'm more familiar with Eureka because I had to do some work out there many years ago. At the time I visited there in exactly the year 2000, so 22 years ago. It had a population of 20,000. Eureka, California. You heard about that. You heard about that town, I'm sure. Los Angeles, on the other hand, has got a couple, 12 million, I think. San Diego, 2.5, almost 3 million people. And I'm not sure the 2.5, I think, is metropolitan. Yeah, for sure. In other words, San Diego and its 16 or 18 cities together. You know, all the cities that surround San Diego. Los Angeles has about 50 or 60 cities, and they all, of course, need the water. So, long story made short, there's a lot of people living in the south where there's no water. How did that happen? I mean, this started to happen 130 years ago when California was being settled. Because as you guys know, California, 1849, discovery of gold, development of the state. But it took 50 years for people to really decide to move to California from wherever they were coming from, right? It also took the development of the train, and I don't want to sidetrack on this, but until the train got developed so they could bring a whole lot of people from the east, from Midwest and east, California wasn't going to develop. So by the turn of the century, say 120 years ago, California was already very well in the process of development. And then the people decided to move south, or to go south, not to go north of San Francisco. Why? Why didn't we follow the water? And the answer is, typically people like dry areas. They still like to shower every day. And hydraulic engineers like us to bring the water, but they don't want to go out there. Very few people actually decide willingly to move to where the water is. A case in point, the Amazon in Brazil. The people in Brazil, 200 million of them, live elsewhere. They don't live in the Amazon. The Amazon is largely depopulated because there's a whole lot of water out there. And therefore, not that many nutrients. And you got to have the water and the nutrients together. Otherwise, you cannot make a living because you don't need the water. The water, you can drink the water, but you don't eat it. What you eat is, and for nourishment, is the nutrients. The nutrients got to be found. That's why I believe that the president of Brazil was wrong when he decided to conquer or develop the Amazon 4 years ago, I believe, when he went in there. And fortunately, he got booted out of office. I don't want to get into that area, but now he's not there anymore. So the Amazon's going to go back to being what it was, largely unpopulated because of the hardship. Why hardship? Why am I saying that? Because the more water, the more the bugs like it. And we're not bugs. We don't like the bugs. The bugs like us. They want to eat us alive, but we don't. So we can't be fighting the bugs all the time. So therefore we decided, now of course, that depends on who are you, because some people are used to, the people who live out there must be used to it. Otherwise they wouldn't be living out there, right? So it matters to determine who are, what DNA and so forth. And I'm not going to get in there because I don't know too much about it. But the point is that the bugs like certain people and not others. That's the truth. I don't know exactly why. I can tell you stories galore on that. So this is the confluence of the Arroyo Pasajero with the California Aqueduct near Coalinga, California. It's about 4 hours from here, roughly. I don't know if you've been out there. I've been there several times because we were studying at the time, this was in the year 2007, 2008, we were studying the issue of the salinity in the Central Valley, which led to a couple of papers on the subject. We have several papers on the subject already. So I was there several times, mostly in the area in the southern part, maybe an hour south of Coalinga. Okay, so now we're going to move on to reservoir trap efficiency. We are going to be doing this calculation of reservoir trap efficiency. For this, we're going to use the so-called Brun curves. People call them just the reservoir trap efficiency curves. Other people call them the Brun curves. I am not sure that I mentioned the name Brun in here. Following procedure to determine trap efficiency. Let me just go in here for a second. 44, USDA Soil Conservation Service, National Engineering Handbook, Section 3, Sedimentation. So from the Sedimentation Manual of the National Engineering Handbook, we took this chart in here, and I do not recall, to be honest with you, if the name Brun, B-R-U-N-E, was mentioned in the manual. But we obviously didn't mention it over here. It must be that the manual didn't mention it. But it's widely known as the Brun curves, these curves in here. And by the way, they have not been superseded. They're about 60 years old, the Brun curves. And that's what we're going to use today. We're actually going to implement an online calculator to determine the rate of filling of sediment in a reservoir. And that's what we're going to do right now. So, okay, if I can catch my breath here. Reservoir trap efficiency. The difference between incoming and outgoing sediment is the sediment deposited in the reservoir. That's obvious. So the sediment is going to move into the reservoir. There's no way we can stop that. And some of it is going to stay in the reservoir. And how much of it is going to stay? What percentage is going to stay and what percentage is going to pass? We know for a fact that a small percentage will pass. Actually, a percentage will pass. We don't know how small it is. That's the rationale for the Brun curves that we're going to study right now. The incoming sediment can be quantified by the sediment yield. In other words, the sediment delivered to a point downstream. That we call sediment yield. The total sediment load entering the reservoir. That can be done in various ways. The quickest way to do that is to use the Dendy-Bolton formula, which is not 100% accurate, but it is not respected. It's well used because it's easy. Remember the KISS principle. Keep it simple. That is an easy formula that the Army Corps has supported in their manuals. So with the support of the Army Corps of Engineers, then we're fine. We can do it. Okay. An exact calculation would take a lot longer. As a matter of fact, I think one of you, I don't recall who, is studying that problem to present at the end. Not exactly, don't remember who, which one of you. But we'll see this subject in 4 more weeks, explained by one of you. The outgoing sediment can be quantified by the trap efficiency. That's the definition by Broom. The trap efficiency refers to the ability of the reservoir to entrap sediment being transported by the flowing water. It is defined as the ratio of trapped sediment to incoming sediment in percentage. And it is a function, here we go, of 1, the ratio of reservoir volume to mean annual runoff volume and the sediment characteristics. The ratio of reservoir volume to mean annual runoff volume. So in other words, if this ratio is high, is going to trap a whole lot. If it's low, it will trap a whole little. Why? Because in the numerator, you have the reservoir volume, and in the denominator is the annual runoff volume. In other words, the quantity every year. So the more the annual runoff volume, the more it'll trap. Am I saying that correctly? Yeah, when the runoff volume is high, the number will be low. So no, the less it will trap. I'm sorry, I'm maybe confusing here. The less it will trap. The trap efficiency will decrease. So the procedure to determine trap efficiency, following the manual, the the NRCS manual, is to determine the capacity C in cubic hectometers. Allow me a little bit of latitude here. That you may have not heard cubic hectometers before, but it is 1 million cubic meter. In the metric system, SI system, 1 million cubic meters is equal to 1 hectometer, because hecto is 10. I'm sorry, hecto is 100 times, because deca is 10, hecto 100 to the cube power, because his volume gives you 10 to the 6. So 10 to the 6 cubic meters, that is 1 million cubic meters, equal to 1 cubic hectometer. Or it can be also done in acre feet. Determine an acre feet, as you guys know very well, is the volume of 1 foot in 1 acre, held by 1 acre. That's the US customary system. Determine the mean annual inflow to the reservoir. Mean annual inflow to the reservoir. So that is the discharge times the time. If it's mean annual, it's the mean annual discharge times the number of seconds, and that gives you the cubic meters. Is the annual inflow to the reservoir in volume. That can be done readily, because the annual inflow to the reservoir is a hydrologic value that can be obtained more or less readily. Okay, use figure 1322 to determine the percentage trap efficiency as a function of the ratio C over I for any of 3 sediment characteristics. Estimate the texture of the incoming sediment by a study of sediment sources and or sediment transfer by size fractions. So we have 3 in here. We have fine-grained sediments, median curve, and coarse-grained sediments. So if you're looking at sands that are like on the order of 1 millimeter, that would be coarse. But if it's fine-grained sediments on the order of less than 0.1 millimeters, say 0.07, 0.05 millimeters, that would be fine. And median is in the middle. That's as easy as that. So the type of sediment, coarse-grained or fine-grained, will determine whether we use the top for coarse and the bottom for fine-grained. If we're not sure and we're in the middle, then we're in the middle right there in the median curve. Okay? So the upper curve is applicable to coarse sands. As I said, the middle curve to sediment consistent with a wide range of particle sizes, and the lower curve to fine silts and clays. Okay, so from here, from this tool that given to us by Brun, we can actually calculate in a ready way, meaning I was going to say quick and dirty. No, I shouldn't say quick and dirty. In a ready way to do. In other words, in a expedient way, because this calculation is fairly straightforward. Although it may not be for you, since it's the first time you're looking at it, it's not going to be fairly straightforward. But once you dig your heels and put your mind to it, you'll see that it does make sense. There's not differential equations in here or anything of that sort. All we have is just a mechanical calculation of volumes and weights with the addition of this curve in here. So that's what we're going to do. The design life of a reservoir is the period required for the reservoir to fulfill its intended purpose. For instance, structures designed by the Natural Resources Conservation Service for watershed protection and flood prevention have design lives of 50 to 100 years. This is something interesting because what is the design life? As I say in there, it's either 50 to 100 years. Why do we choose the time 50 to 100? Well, ideally, it's been said that 50 years is two generations and 100 years is 4 generations. And we certainly, these structures are costly. So we're going to pay for it. We're going to amortize the cost of building the structure in a period of time. And we can amortize it in 25 years or 50 years. But once it's paid, it's paid. So the rationale, one of the rationales, or in other words, one of the explanations is that we shouldn't be paying 50 years for a reservoir and then have the next generations use it for 500 years. So 500 years is something out of the question. 50 to 100 years is the standard, the how can I say, the way we do it currently. But that's interesting because it brings all kinds of discussions out there. For instance, here in San Diego County, we have about 10 to 12 large reservoirs that are holding on to the water from the runoff. And it occupies, or it's used for about 30%. I believe the number is correct. We can check. This number does vary a little bit. We can check with the local water provider, the San Diego County Water Authority. But I do believe that 2/3 of the water is imported. About 1/3 coming from the Colorado, another 1/3 coming from the north, and the 1/3 that is not imported is local. Is coming from the 12 reservoirs that we have. Names: Morena, Sweetwater, this other one that is being repaired right now. I can't remember the name. I'm really bad at this one. So there's 12 reservoirs. You may not have heard of all of them, but you certainly have heard of some of them. Hodges is the name I was trying to remember. Hodges is being repaired at this point. Why is it being repaired? Hodges is almost 100 years old. El Capitan is 100 years old. Capitan is only about 20 miles northeast, I believe, of San Diego State campus. El Capitan, Morena is also very old. Morena is about 110 years old, if not more. I believe turn of the century, Morena, 120 years old. Why is it that these dams are so old and they're still being operated? They're still in operation? And the answer is, I don't know. I'm not a politician. In order to decide the reconstruction or rebuilding or destroy and rebuild, you have to be a politician, handle the money, decide what to do, right? I'm not in that category. But the point is that we have a whole bunch of old dams here in San Diego County. Many of them are 80 to 100 years old. They should be, in the ideal world, they should be retired and rebuilt, reconstructed. But we're not living in an ideal world, and some of them, Hodges, for instance, is being repaired. When I was there, maybe many years ago, I took the students. I noticed that there were cracks and the thing was leaking and so forth. That was 20 years ago. It's taken them 20 years to figure that out. I don't know. I can't criticize them because, you know, they do their job. People do their jobs, and I don't get involved in those jobs. All I'm telling you is that 20 years ago, when I was out there, the dam looked like it needed extensive repairs. That was 20 years. And 20 years later, now they're fixing it, hopefully for good. Okay, so the decision as to whether destroy the dam or bring it down and build it again, that's somebody else's decision. But I'm telling you this because what's happening here in San Diego is we've been around for 100 years. San Diego was founded around the turn of the century, I think. Okay, and the infrastructure, and the water infrastructure was the first infrastructure they put on. Without water, people don't come, right? So we've had these dams for water infrastructure for roughly 100 years, and now they're getting old, and we need to consider doing something about it. Okay, provisions are made to guarantee the full design water storage capacity for the planned design life. This may entail, one, cleaning out reservoir sediment deposits at predetermined intervals during the life of the structure, or, as is more often the case, providing a reservoir storage capacity large enough to store all the accumulated sediment without encroachment of the design water storage capacity. Usually, the ballpark number there is 20%. In other words, after the 100 years of usage or predicted usage or predetermined usage, you should have 20% full of sediment so that you can still operate the 80%. That's a standard in any book. Whether that actually happens, I do not know. It depends on the actual location. I think I know one of you is doing a study of sediment deposition. I don't recall who. So he or she is going to tell us a little more about sediment deposition, practical, actual sediment deposition, because every one of these dams has a history of data collected by the city or the county, depending on which agency is the one that is operating. In the city of San Diego, most of them are operated by the city, by the way. Typically, calculations of sediment filling rates and sediment accumulation are part of the design of reservoir storage projects. Yes, correct. So that's part of the things that we study. Distribution of sediment deposits. The distribution may be such as to materially affect the operation and maintenance of the dam. The amount and types of sediment deposits vary with the nature of the sediment itself, the shape of the reservoir, the topography, or bathymetry. Bathymetry is the topography underwater of the reservoir floor, the nature of the approach channel, detention time, and purpose of the reservoir. There are hydroelectric reservoirs, there are reservoirs to hold water, there's reservoirs to make the water rise to a certain level. There's all kinds of usage for reservoirs. The coarser sediment sizes are the first to deposit in the vicinity. We already had said that. We showed the graph. Finer sediment sizes are able to travel longer distances inside the reservoir and deposit at locations close to the dam. Very fine sediments are usually uniformly distributed in the reservoir bed. I have in here an example of sediment deposition, all right. This is the sediment deposition at the tail of Torrata Reservoir in Cuajone, Peru. I was invited to go to southern Peru, Cuajone, 2 or 3 times. I don't recall if it was 2 or 3 times in the last 20 years. And I was able to take this picture. As you can see clearly, they have a dam over here. The dam's over here. And this dam is for the purpose of supply. This is a mine, by the way. It's not a city. It's a mine. It's a large copper mine, one of the larger copper mines, I think, in Peru. And Peru is busy extracting the copper for world usage, by the way. One of the primary producers of copper in the world, in Peru. So the mine over here has a large dam out there. Well, it's kind of a mid-sized dam. It maybe 50 to 80 meters. It's kind of high. And it accumulates this amount of sand. This is in the entrance to the reservoir. This is all sand that has deposited. And the question is, what to do with the sand? And the answer, what the mining company is considering now, and I believe they already operated on this, is to take some of the sand and remove it and put it somewhere else in the vicinity. They don't want to transport it because this is a place where it's in the boonies, you know, a mine in the middle of the Andes. So in order to transport that sand somewhere else so they could sell it, it would be costly. 50 miles, 100 miles, something on that order, maybe kilometers. And yet there's not a whole lot of industry, building industry out there to justify it. So what they need to do is to take this sand out of here and hide it somewhere else. It's good sand. I mean, if I needed sand, I could go out there and pick it up and take it with me, but it's too far from everywhere. So the transport is going to be expensive. So that is one of the issues. So sediment detention basins or debris basins. We have already discussed this earlier in connection with the experience in Santa Barbara in the year 1991. sediment detention basins or debris basins. But by the way, I do have the video, and I'm going to put it up for you guys to see if I have not done so already. Or else the better thing to do would be to show it the next time we meet, which will be next Tuesday. It's a 10-minute video. Sediment retention basins. Now, what's the difference between sediment detention and sediment retention? Not a whole lot. Both of them are going to detain and retain the sediment. I've seen both usages, by the way. Some people prefer one and some other people prefer the other, but I don't really, at this point, I don't have a strong opinion. Sediment retention basins or debris basins are small. They're also called debris basins, are small reservoirs located in upland areas with the specific purpose of trapping sediment and debris before they're able to reach the main fluvial network system. That's the experience of Santa Barbara in 1991. Debris is a general term used to describe the assortment of cobbles, boulders, branches, and other vegetative material that may clog channels and hydraulic structures. I have a couple of movies of debris flows, which are phenomenal. I'm going to share them with you also. I did not take those videos, but I have them on my site. I was able to grab them from YouTube or actually show them directly from YouTube. I think they're interesting because it would be an extremely rare situation for any of us to actually see those debris flows. You have to be there at the right time, at the right place, doing the right kinds of things. It's difficult. I actually have not done it. But I have several, actually. I have several, 4 or 5 videos of debris flows that have happened throughout the world, actually throughout Latin America. I don't usually get, I shouldn't say that. I get them from throughout the world, but mostly from Latin America. I've got 4 or 5 from Latin America recently, by the way, a couple of Argentina, in Bolivia, etc. In Bolivia, there's one river out there that has the how can I say, the knack for sending these debris flows every couple of months or so, huge debris flows. It's one river. So that is interesting because it's unique. Most of the times these debris flows are distributed throughout the world. You know, it's happened here and they don't happen again in many, many years. Okay, so that's debris flow. I wish I could have that, but no problem. I'm going to show it to you next time we meet. So debris basins are placed upstream of channels or reservoirs with the specific purpose of temporary detainment of debris. What do we do with that afterwards? We have to remove it. You have to take it out to the dump or whatever. The owner, the operator has to handle that. Debris basins are usually small and designed to be cleaned out from time to time. Some basins are sized to fill up during 1 or 2 major storms, like in the case of Santa Barbara. Others may have a 50 or 100-year design life. Project costs and site conditions determine the size of debris basins. Interestingly enough, in Santa Barbara, which I told you there was one classmate and one student were actually in charge out there. My classmate was the boss, the head of the district, the flood control district. And my student was the guy that was doing the design of the debris basin. So they designed the debris basin with a certain size, of course, and everything. And they had to do it quickly. They did it in about a couple of weeks, piling up, you know, the construction material and so forth. They were against the wall because they knew that the rains were going to come. And they were working at the end of December, January. It's all described in the video. And they knew that anytime the rains were going to come and they could have been stuck in the middle of a mess out there. But no, they were lucky. They were able to finish the project. They knew, not only lucky, they knew what they had to do. They had to finish the project before the major events. Of course, you never know when the major event's going to come. If we knew, that would be better. But the fact of the matter is that they finished the project, I think in January or February, and then the miracle March 1991 rains came. Why do they call it Miracle March? Because California was undergoing a drought, and the drought was 87, 88, 89, 90. There were 3 or 4 years of drought out there. The record will show that it was a long drought. So it was just a matter of time when the big flood was going to come, because long droughts are typically followed by very sudden floods, because nature's got to reset the system, right? 4 years of lack of rain, and then one event where the whole thing dropped on us. And that's exactly what happened. That's what that is called, a miracle March. It was a miracle because it had not rained for 4 years, excuse me. And it was a lot, but these guys were prepared and they were able to sustain or hold on to the debris in the debris basin. The only thing that was interesting was that they built this debris basin with X amount of volume, right? I don't remember right now. And it turned out that actually, I think it was 2 debris basins in different watersheds. But anyway, as the story goes, they filled out 50%, which is good. Remember, in sediment calculation, you can afford to miss it by 50%, which is depending on how you look at it, it could be 100%, 50% on one side, 100% on the other. So they missed it to say by 50 to 100%, and it was fine. And on the side of safety, the debris basins did not fill up. They actually filled up to the middle, which was good. I consider that to be a tremendous success. And I am actually very proud that one of our students, top graduate, 1985, was able to do that in 1991, 6 years out of school. That design, the particular design of the debris basin. Okay, so sediment yield determinations. This is interesting. This comment is interesting, and I'm going to finish here. Sediment yield determinations for debris basins should include both short-term and long-term analysis. This is interesting, and I'm going to comment on this right now. What is short-term and long-term analysis? The long-term sediment yield is determined from the appropriate sediment rating curve. For infrequent storms, the sediment concentrations may exceed long-term averages by a factor of 2 or 3. Where did we get this information? Let's look. U.S. Army Corps of Engineers, 1987, Sedimentation Investigations in Rivers and Reservoirs. Engineering Manual, this is a series of the Army Corps of Engineers, okay? So you can't be more authoritative if you consider that the authority of the Army Corps, which is correct, okay, that for this statement, which I pulled directly out of the manual. What they're saying is this, that you better be careful, because if you have long-term data, by the time you're actually looking at an event like the event of the Miracle March in Santa Barbara, you would have to consider that you could have a possible error in the sediment transport by a factor of 2 or 3. So basically, they have confirmed Professor Ponce's statement earlier that I said that you can miss it by 50% and still be okay. And you should be prepared for that. That's what the Army Corps says in their manual. You can miss it by a factor of 2 or 3. So therefore, you better be careful. If your calculation shows 50, make it 100 or 150, because that's what you're going to need, or vice versa on the other side too. But in this case, they're talking about more, not less, by the way. So that's basically it. So what we're going to do next time we meet Tuesday is we'll go over this example. And I'm going to ask you that you go over the example before we meet, so as to facilitate my explanation of it. This looks easy, but it is not easy, okay? So spend some time, please spend some time on it, maybe 10, 15, 20 minutes over the weekend, trying to make sure that this whole thing makes sense to you. Because if it does make sense to you on first or second reading, then it'll be easy for me to explain it to you. Otherwise, we'll have to spend a lot of time, or else I'll just have to say, so be it. Read it and hope to understand it. Because like I said, it is intricate. It looks easy, but it isn't. So with that, I am going to stop here. And I will see you next Tuesday in the customary time, on the 13th week of this class. Thank you.